hear me? Okay, good. All right, I think it's time to start. We would like any questions from our lecture on Wednesday. I got a few emails from students who had to be absent today. So the people and not these two individuals had to be away for very valid reasons, obviously. And they asked me of what I was planning to cover in class. So for all of you, in case you have that, the best way to see what we cover in class is to go to whatever week we are on. Okay, well, it's supposed to go to, what happened? Ah, there it is, takes time. So yesterday, the last 2 days, there have been some issues with Canvas. Do you know that? Okay, so in case we cannot access it, we'll figure it out. But so you go to say week 1, and then you see here what we covered by day. And then what I will do at the end of today, for example, so you can see it, I'm gonna go here, and then I'm gonna list. Now I'm not gonna write a lot of things. I'm gonna list what we did, and I'm gonna add things that are not here, but and then what to do for you. All right, the things that I believe are important for you to remember. So instead of asking me, and I mean, you can ask me always about anything, but in cases you ask me about what we're gonna do today or what should I do myself, I will always send you to this website. Okay? So for today, if you want to see what the plan is, today is to introduce the Top Hat. I hope that many of you had the opportunity to do that. And so I will try to access it from here. So practically for you to make it easy, you go back here. This one, the first one is for class because each one of you is in a separate class. Sometimes the problems may be slightly different, but they will be on the same topic, all right? That's why I created 2 separate groups. And also it was important because the times for the various sections are separate. Now, what the plan is to discuss during office hours or on Sunday. You see, office hours, my experience has told me that office hours are useful right after the class for the first 2, Monday and Wednesday, but on Sunday. You cannot imagine how many students need support the last 2 hours before the homework is due. Now, it's never good to be under that pressure, but life is what life is. And a lot of times we all try the last minute to do things. And I've been one of them. And I cannot expect you to be better than I have been in my whole life, all right? So there is always a reason to have some questions. So on Sundays, I always have a 2-hour opening between 3:30 and 5:30 for you that you may have some last minute questions about the homework. You need something, you get stuck with something, but you're not gonna have enough time to start solving the problem then, all right? That's why I put it late. I could have placed it Sunday morning, but I did not do that because I don't want you to wait until you speak with me on Sunday morning to solve your homework. It's gonna only be for that last minute kind of getting stuck with something, and then you need somebody to push you a little bit out of that place. Okay, so here for this morning, what you're gonna see from your end is whatever exercise I make available to you. So practically I will do one right now and I will leave it open over the weekend. So you have the time to go. For those of you who had difficulties, you know, the first one always we expect some trouble a little bit. And also because this is a review question, and that's gonna give me an opportunity to talk a little bit about things that you need to review or review along the way, because we're not gonna cover them here, things that you have seen before, all right? So this particular exercise, let me see. Let me remove this. I'm going to this one. It says here, vector relations. I'm sure you can see better than I do. It says vector relations and vector identities. Have you done those before? Do you guys remember doing vectors? Okay. So in the book, that's one of the things that I liked in the book. Part 1 gives you a review of everything you've done before, talking about vectors, the basic vector identities, the basic coordinate systems, basic stuff. What I want you to do right now is not necessarily to go and read the whole thing. Just go through and see what the book has, because all along the way, you will need this information. And I would suggest that whenever we solve things and then you don't necessarily remember, I give you, say, for example, an electric field in the XYZ coordinate system, but for you to do something, you need to put it in cylindrical. I don't expect you to remember how to go from X, Y, and Z to rho and theta, all right, or phi. I expect you, however, to know where to go to find it. And the best thing is to go to your book. Don't go necessarily to Google immediately. You cannot believe how many mistakes I have found on Google, because there are a lot of different blogs. It's not like there are mistakes. People are saying things which are not necessarily true. There are a lot of students who are adding to these blogs, and then at one point something either is not well explained or is wrong. So don't take anything from the web. We all go to internet, all right? We all go there to see things, but be careful of what you're using, and also use your judgment. Try to make sure that it's correct, but the book is correct. So go to the book first, and then if you not find something that satisfies your needs, then either speak with me or you go and look, but be careful with that. So anyways, the book has all of this in the beginning. So that's a good place to revisit throughout the class. I don't want you to go right now and say, read this. Now, the first exercise is gonna help you go back and remember some things about vectors and why vectors are important. Why vectors are important in this class? Because vectors show direction, all right? So for example, it's like you have a car and you talk about the car, you talk about its velocity, but you don't say which direction the car goes. That's very important, all right? So usually if you want to characterize a car in action, you need a vector, all right? Velocity is a vector. That's why it has direction. Electric fields and forces have direction. So for example, what is a force? If I am attracted, say, let's assume that was possible in a different universe, right? That our mass, biological mass, was attracted by some kind of a surface. If I'm attracted by a surface, then the attractive force is going to take me into one direction. I'm not going to feel a force and then be steady, all right? The force moves you, like gravity takes you from here. Gravity. For us to be able to understand the forces, electric and magnetic forces, and then understand the fields, we need to have direction. So vectors are extremely important. Number one. So feel comfortable with vectors, all right? And there are particularly two types of properties in vectors that are important. Summation, also summation is the same with subtraction, all right? It's just a negative sign, but a summation or subtraction in one, and multiplication. And you will see the multiplication later, what it means. Right. So, example. All right. Now, this is kind of interesting. I will show it to you. It says, it gives you two vectors, A and B. And these vectors, they have in between them an angle theta. And then it says, assuming, this is just for a review, right? Assuming that theta is 90 degrees, which of the three identities are correct? So here, before you get into math, that's what we're going to do in this class. You remember when we said math is a language? When I tell you come, you don't look whether it's C-O-M-E. You try to understand what the meaning is. So when you see A plus B, what does it mean? It means the sum of two vectors. So you have to understand, you have to remember that. All right? It's not A plus B, A plus B, the map. In my mind, it means if I have two vectors, and if somebody wants me to sum them up, and they are vectors, they have directions, how do I really do that? Number one. Why is this important? Because you will see, if I have an electric field from one source like this, and if I have another electric field from another source charged like this, and I want to find the total electric field, I have to take the sum of the two. That's why it's important. All right? If your A is the direction of one electric field, and the magnitude, it shows one electric field, and B shows another electric field, A plus B is going to be the total. You got that? That's why it is important. It's not just a sum of two vectors. So here it says, and A minus B, what does A minus B mean? It means that if one field, if the two fields are like that, then A plus B is the sum. But if this field were to all of a sudden flip direction and go like this, the new field B is going to be minus the original B. So the new sum of the two new vectors will be like the subtraction, the A minus the original B. That's why A and plus and minus belong to the same category. What does minus mean? That one of the vectors has flipped its direction by 180 degrees. All right? So that's how you're going to think it here, not math. Think it in terms of entities we are going to use in this class. All right? Always think, if you see A and B, this is a field. Don't think it's a vector or mathematics. That is the kind of transition we have to do in this class, and it's gonna make you understand all of this in a much better way. You're not gonna get confused. So, if now, what does that say? That if that's the case, then the sum of the two vectors A and B, it is possible to be less than the sum of this vector and the other vector, which has the direction, right? 1 So that is this A plus B, these vectors will have a sum. So these two fields will have a sum. The total field out of those two units will be smaller. It is possible that it can be smaller of the total field between A and the inverse of B. Or it could be equal, or it could be larger. Of course, if you have two numbers, all right, one of three things happen. Either one is bigger than the other, A is bigger than B, for example, numbers. 1, 2 is bigger than 1. Or they're the same, or the other is smaller than the first one. All right, there are three possibilities. So that's what it shows you here. So you have to find out which of the three applies for this case when they're 90 degrees. Which of the three applies when angle theta is less than 90 degrees? Which of the three applies when theta is larger than 90 degrees? That's all. If you go to your book and look at these, then you're going to quickly find out what's happening. And also graphically, you can understand how this is going to work. So, a lot of people are better looking at equations. I'm more of a graphic person. So if you do it correctly, graphically, it's going to become obvious. So this is a kind of a problem that I will give you. If, for example, we were to just have this material in the morning or during the lecture, that could have been, if I had already told you, or that what is happening in this case is during the lecture, I could have given this to you as a very quick exercise at the end of the lecture. Now I'm giving it to you, and I'm giving you time over the weekend. All right, so I will turn it off on Monday morning. I give you that because I want you to review it also, because this is material that we're going to use for this class. All right? Any questions about this? So if I give it to you, if I give you this, and then I'll go back to your lecture also. Let me see. I'm going to your section rather, and we have the same. This is for the quiz. There. So see what I do from here? What I do, I can go, let me see, move this one. I will go here and say assign. When I say assign, for now, I will give it to you and you're gonna get points. For those of you who will do it, they will get 60 points, 30 for doing it and 30 if you do it correctly. All right, so I assigned as homework, which is graded, and then I will do assign. If you go to your account, you should see it. And tell me whether you can see it. And you have until Monday morning. Okay, it's a multiple choice because you see here how it goes. It has 3 questions. If one applies, you have to move those. All right, you have to move the appropriate answers. So play that with a little bit. It's an exercise. I expect you that everybody's going to do it correctly. If anybody had a technical problem, I'm not going to penalize you. All right, this is an example. Probably everybody's going to get a 60 unless it's a reason that I cannot approve. All right. Any questions about this? And as a matter of fact, we can see how the class has done. A lot of those is for me to get a sense also. All right, any questions before I move to the next topic? Yes.
If I open the quiz, is it like a time at all?
There's no time on this one.
No time on this one?
Mm-hmm. The time on this one is I will turn it off because I have not assigned time.
Okay.
So personally, I will turn them off. Okay, I don't like to assign time because we are doing real time and something may happen. There may be a question. If I assign time, then I have to go inside and fix it again. So I don't assign time, but I turn it off and I turn it on. I will turn it off Monday morning before I come to this class. Okay. Any other questions about this? All right. If there are any technical problems with this, I've never had a problem about this. This website is always up. Tell the truth, this is probably the 4th year I have used it. I never had a case where I needed to go on it and it was down. But if you have a problem, if Canvas cannot connect you, then we will deal with this. All right, so now let's go back to our class. Make sure that I'm also good with time. And now I would like to discuss with you. Go back. All right. We go to week 1. And now we are fundamental forces. Okay. And why do we start with fundamental forces? I don't know whether you have been aware of this. I'm sure that at some point you have discussed it, but there are 4 primary forces in nature. And a lot of times, people are placing those in a different, with a different arrangement. I place them here by the way we think today that our universe was created and what forces created the universe. Now, the closer we go to time 0, the less we know, all right? That is the point where our capacity for understanding stops at time t equals 0. Maybe at some point in time, way after maybe my lifetime, people will learn more, but the learning as we go from time t equals 0 plus, which is right before time t equals 0 to time t equals 0, this delta time, all right, is like our understanding is practically infinite. Our misunderstanding, rather, infinite. Our understanding is 0. There are a lot of things that we have not been able to comprehend, and definitely a lot more things that our existing set of understanding nature and equations have the capacity to address. However, with what we know today, the initial force that created our universe, it's a weak force. So I will say that. The next important force that created our universe was the electromagnetic force. The next one was the strong force, and the final was gravity, the way that they expressed themselves. And all of these four forces are holding us in one place and make us who we are. This is so important to remember. This is why we exist, among other things. This is the fundamental. Without those forces, the universe would not have existed in this form. And we would not have been here the way we look and sound, all right, obviously. All right, the weak force. What is the weak force? In fact, I will go for the weak force specifically because I thought it's something that is important for you to remember. I will go back and I have a document that I will like you to read because it's so interesting. So, what the weak, at some point in the beginning of time, there was one neutron, one particle was created. Maybe more than one, but that one, that type, right? The cluster of particles. And what happened? Due to this weak force, all right, within the neutron, there are other particles that people have tried to speculate. But in reality, these weak forces inside the neutron gave rise to one electron. So in the beginning of time, there was a neutron. That's how we started in life. And then, because of the weak force, a neutron produced a proton and an electron. You know how fundamental that is? That means in a neutron that has what? 0 charge. Right? The total charge of a neutron is what? How much? 0. So at that moment in time, that we had 0 charges because of the presence of that weak force. What happened? The protons and the electrons separate. And what happened? There was always, they call it anti-neutrino, but in reality, there was energy that was weak. That is called decay. All right, we talk about decay in materials, and archaeology is using to measure how many years back something was made. That are the weak forces that lead to this decay because produce out of something, out of 0, 2 things. Out of 0 charge, these produce 2 charges, one positive, one negative. What happens when you have one positive and one negative charge? There is an attractive force. That's why electromagnetics come into place. The moment the weak force created from the neutron, this, then immediately there was an electromagnetic force that kept these 2 close enough. By keeping electrons around a proton, depending of course on the charges between the 2, what happens? You have an atom. So the weak force created this, the electromagnetic force created the atom. Okay. Then the other force, we talk about is the strong force. That's the nucleus in the nuclear force. What happens when you have many protons together? Instead, if it were only the electromagnetic force, what would happen to all of these protons? Will all go away, all right? But no, there is another force which is called strong nuclear force that keeps protons together. So a lot of these protons that came out of neutrons, they came together. And then while they were together, this force expressed itself and got them to come very close. And then what happens if you have many protons together? You have multiple of these electrons come around. So you have atoms that are different, right? Different protons, different electrons, different atoms, different materials. Okay, that was the nuclear force. And the last one was gravity. Why? Because when many atoms come together, they create a molecule. When many molecules come together, they create mass. Because each one of these, the proton has mass. The electron has energy. What happens when there are masses? There is gravity. That's when then the last force was expressed. All right, so there is a reason those forces came one right after the other, of course, in a very short period of time. I don't know what that means anymore. All right, I don't know what time means anymore when you go there. But you need to remember that this is how these are the four forces of life. Okay, that have made us what we are today. And very important, obviously. For many years, people were thinking the electromagnetic forces like the last ones out there. No, there was a time, again, I don't know what it means, but there was a time, after time, people said, well, the electromagnetic force and the weak force were almost equal in their making of the rest. And of course, the gravity is the last, keeps the galaxies together, keeps the systems, the solar systems together, keeps the whole thing together. Now, all of these forces, they come and go. It's like one generates all of them, and all of them go back to one. And you see that in some places in the universe that we have not understood very well, like black holes, how you go from mass to energy. We know, for example, all of these theories, how you go from energy before the neutron to mass. But how you go mass to energy, which is a black hole? The black hole is a big transformer. It's like, have you seen those when they cut the leaves? It's like they have a huge thing that all of they absorb all of the leaves, and then it comes out of the other end like tiny pieces. That's how the black holes are. They absorb all of the mass, and mass can be a whole galaxy that is absorbed. All right, they absorb mass, and then they create energy, and it's like the energy goes out in a very narrow beam, and as a like as a beacon. So practically, the black holes are like huge transformers. They keep the balance between mass and energy in the universe. But there is a lot that we don't know yet. All right. So maybe later in your lives, all of this may change to something different. But so far, this is what we know. So this is what is important for us: the force between the charges. Okay, so the next question that a lot of people are coming to me and are asking me, so let's go back. So now we covered this, but I would like to, here, for example, they explain this. Please read about the weak force. This, I found it in Science, and Science I really trust. So I copied it for you. I like stories like that from NASA educational website because it's all correct, or from Science. But then we are going back now to fundamental forces, because I want to go to the end of it. Practically here it explains the forces, electromagnetic force, okay? what is responsible for example, this is what I like in electromagnetic force. There are, of course, there are two, when we call electromagnetic, we mean really three different instances, same force, but expressed in three different ways. Not a different force, it's the same, the nature of the force. But when we see, we understand three separate things. Sometimes we thought that there were three separate, they are not, but in any case, that's how it is presented to us. One is the electric force. So I have one electric charge positive, I have one electric charge negative, and they attract each other. Or I have a positive charge and another positive charge, and they repel. Okay, this is the electric. Then is the magnetic force. That's the difficulty. The magnetic force, magnetostatic specifically, when we saw it, we never thought it was related to the electric force. But the magnetic force is something that is generated while the electrostatic force is generated by a static charge. The magnetic force is generated by a charge that runs with a constant velocity. So it's a charge, but it runs with a constant velocity. When a charge runs with a constant velocity, what do we call that? Current. So a constant velocity means DC current, right? There's no change. So the static charge, electrostatic force. A charge that moves with a constant velocity, magnetostatic force. We call it differently because when there was no reason to call it differently, but when the fathers of our field were able to understand that those exist, they had no idea that they were related. They observed them separately, right? They observed them when even before they knew about charges. So you take, for example, the ampere, and people were using ampere for the old days for like jewelry and stuff like that. And then you try to shine it with, that's what they did, try to shine it up, and make it soften everything smooth with cloth or paper or something else. And that brought all of the charges on top. And then they could see that it could attract small things, right? That's how the early sense of something bad became, people understood that. So very early. However, they are the same kind of thing. Now, when a charge moves with a varying velocity, so it has an acceleration or deceleration, but it changes, the velocity changes, then what do we call the field it creates or the force that is generated from that? Electromagnetic. Why do we call it electromagnetic? Because it's a combination of the other two forces, but in reality it's one force. It's just that we understand it in the form of two forces. So a lot of times people will talk about electromagnetic force and they will show you electrostatic. This is where I know that it's electrostatic, magnetostatic, and electromagnetic. In reality, we call it differently, but it's the same. All right. So why I love this? Have you seen this before? Do you recognize this is Earth? Right. What are those lines? Around here, what we have? We have a magnetic field. Why do we have a magnetic field in here? Do you know about that? Have you anybody yet? Yes, because we have a fluid core that is moving. All right, it's like if you take a bottle and you move it, the fluid in there, because fluid is going to start moving. But this is iron. It's full of iron. And it's like the iron's charge. So they spin like this, charges. And what happens if they spin with almost constant velocity? You create a very strong magnetic field. Okay. So what is the good about our magnetic field? would we be able to live on this earth without the magnetic field? What do you think? Why? What does it do? Yes.
It shields us from the sun's radiation.
Yes. What does that mean? Radiation means particles. When we say radiation, practically there is a particle, right, that comes out. Look at this. With on the surface of the sun, there is tremendous nuclear activity. I mean, tremendous. The sun is like a nuclear bomb at the center of the universe, and thank God it is, because the Mars is so big, not big, not too big to split, but big enough, it keeps it in one piece. All right, that's good enough. Then there are nuclear explosions constantly. I mean, it's like you have a nuclear plant in the center of our universe, right? And then it's constant nuclear. What happens when you have nuclear explosions? There's all of these gamma particles and alpha particles, and every particle that you can think is radiating. All right. If these particles were coming to our body, we would be dead early on. Because what particles do, and that's when you die from nuclear radiation, right? I mean, if there is a nuclear accident, like in Chernobyl many years back, there is in fact a very interesting video. It was a documentary I saw on Netflix about the Chernobyl incident. But what happens is you die because these particles enter your body and then they destroy your organs. And they destroy it. And so we would have, there would not be life on Earth. All right, if that could happen. But look at what happens due to the magnetic field. These particles, that they are charged also, the magnetic field expels them. And they go around Earth. You see that? They come here and they hit us really hard, but they don't make it through. So it is the magnetic field that really helps us in that regard, which is amazing on how, those things work. So in any case, all of these are important because the fundamental thing here for you to remember is to connect the concepts in this class to things that you have experienced before, or things that you have visualized, things that make sense to us, all right? We're not gonna keep it abstract because it's not this abstract. If we keep it abstract, you're not gonna remember anything about electromagnetics after you take this class. All right, nuclear force, we talked about this, gravity. All right, now, the last thing about gravity, gravity is the one that we have understood the least. Even if we have found gravitational waves, but we don't understand how gravity works. As a matter of fact, we don't know how these forces are exerted in distance, right? So take the electromagnetic force so what is the electromagnetic force? As you know, you have a negative charge, you have a positive charge that attracts it. For us, the only way to feel force is if I come and push you. And there is exchange of mass. All right. So we cannot understand force without understanding that there was a mass involved. But this mass involved in electromagnetic force, what do you think? Think on how we communicate with satellites who go to Mars. Okay, you have seen it in the news. In NASA, they got data from the satellites that went to Mars. How did they get the data? They had a radio. What did they do with the radio? They had a radio, a receiver, and a transmitter on both sides. And as the Mars Explorer, whatever they call this, collected data from the sensors, it made the data bits, right? Changed the analog to digital, and then modified an electromagnetic wave on the receiver end, on the transmitter end, and sent this data to Earth, to one of our, telescopes possibly, or depending on how far it was, or another station that they used to collect the data. So how did the electromagnetic waves came from that satellite to Earth? Was there mass in between? No, there's vacuum. So how there is an electromagnetic force without mass in between? I mean, on Earth we see forces, but mass in between is the wind, for example, and there is mass in the wind. We see the tidal waves, huge forces. We see the volcanoes that throw, those things all around. We see all of these things, but there is mass involved. How is it possible that electromagnetic waves propagate without mass? So, as a few years ago, nobody knew it. You could hear all the theories. I have to tell you, my whole life, everybody had a theory, however, and we're all wrong. Because those forces do not need mass to be exerted. People have identified, maybe that's wrong, I say that may change, but they think that there is a new type of particle which does not have a mass, and it's called boson. And these particles are responsible for exerting this mass, this force, all right, for transferring the impact of those forces. And they don't have mass, and therefore they can travel extremely fast. All right, otherwise mass does not travel as fast. So you need to keep in mind, you don't need to have an atmosphere for electromagnetic waves. It can be in vacuum. So that is the other thing that we understand right now, at least for that. But a lot of times, especially in this class, we don't talk about forces, even if force is what we feel. All right, force is the thing, the real thing. But we talk about field. So the question is, what is a field? The field is not real. The field is a mathematical construct. What does that really mean? It means that for when I say that I have my phone, and my phone is operating, it's you see I have a connectivity LT, and we may have the ability to speak a little bit about that at the end of class. It's an LT kind of a modulation of a way that we communicate freely. Anybody can call me right now if you have my phone number. So when I talk about this operating, and when we design those things, we don't talk about the force. We talk about the fields. Because it's difficult to start. The force involves two entities. All right, so the force, if you remember, for the initial electromagnetic force, we had an electron and a proton. Okay. To be able to talk about force, you need two partners. For me, I am at the transmitter right now. I could not talk about force unless there was a receiver involved and I knew who was sending me information, or I was receiving the transmitter and the receiver. I mean, we both do the same, transmit and receive. So, but I need to know the partner that I'm communicating with at any point in time to talk about, that force. And then if I were to describe whatever in terms of forces. However, we don't want to do that because a lot of times we are looking at the impact of one source. In a force, you need a source and you need an observer. You need to have information. For example, if the electromagnetic field is exerted between a charge here and a charge in Weisenbaker, then the response was going to be tiny, but it will be. Then I need to know information about this other charge, but I have information only about what here I am. So a lot of times people decided, well, no, we cannot work with forces where you need to have two entities well understood. We can work with a field, with distance means that I only need to know the source. I only need to know one of the charges to be able to understand what this one charge is going to do to any other charge around it. All right? And in this case, to be able to introduce that concept, we talk about the field. So, now that we have talked about that, and who is going to tell me from basic physics, if you remember, how do I go if I know the electromagnetic force, the electrostatic force? I have two charges, Q1 and Q2. All right? I am Q1, you are Q2. So we have these two charges, equal and opposite. Now, if the electromagnetic force was, the electrostatic force was F sub E, how would I go and talk about the field that this charge I generate? I would have to take that force and divide it by Q2. All right? So E would be F electrostatic divided by the other charge that I want to get rid of. So all the information that remains, it only involves information about me, who are the source. So the field, rather, as an entity, does not have a physical meaning. However, for us, we try to find a meaning and we use it in the following, by creating the following concept. We say, okay, if the field is real and measurable, then if the force is real and measurable, the field then is the impact that one charge can have on another charge, even if I don't know this other charge. All right, so it's not measured, we measure it indirectly, obviously, all right, because we measure electric fields, we measure voltages and all of this, but in reality, it's a construct that we create. So do you understand the difference between the field and the force? So if you want to know what is an electromagnetic field and how do you have waves going like that, and what does these waves mean, you need to remember the following. The field is nothing else but the force I create if I am a charge. That's all good. And how we feel gravity, think of gravity as a force, the other force is similar. If I was a charge and people a charge will feel the same kind of, now the floor stops me from going through. As a matter of fact, what stops me from going through the floor? The gravity holds me down. What stops me from going through? Which force? Which force? From the four forces we talked about. Yes. The electromagnetic force holds me in one piece. Otherwise, there will be particles everywhere. And it stops me from going through. So, all right? So I would feel the same thing if I had this glass. We were two charges and we had this glass in between. I would probably go and stay at the glass. I would be attracted all the way up, something would stop me. It's happening to gravity. That's how you need to think it through. All right. So what I would like you to do for this week, look at, make sure you can connect, number one, the top hat and do this problem, review a little bit about vectors. All right. This summation, subtraction, and eventually you will see also product, very important. Then read this material and try to understand, because we'll talk about fields, to get the sense to feel comfortable about what the concept is, all right? And also do your assignment, which is on the syllabus. And I have made all of the corrections on the syllabus we talked about. And I want to thank those for reminding. Okay, any questions? All right, ready to go. Thank you. Yes.
So I just want to confirm. So I just did this question. I just want to confirm if it was right. I actually said number two because it's the same point, and if you just change it on the inverse, it doesn't really change the angle.
So what angle would you?
I said A is the correct answer. It is just 90 degrees.
Two applies.
So,
Yes, you're correct. You're
correct.
correct. Yeah, good. Good thinking.
So I went ahead and did the assignment.
Yes.
But when I was filling it out, I had originally put B, A, and then none, and then C, or like if 3 applies, I wanted to put C. But then I hit submit, and right as I hit submit, these two just switched for like no reason, and I wasn't sure like why that happened. But this isn't really what I wanted to put.
Can I? Okay, let me go back. Could you send me a? Could you do a screenshot and send it to me?
Yeah.
Because I will need to go and see. I don't.
Okay,
I'm
I'll
not
email
figuring
you and
yet.
just explain
Yes,
it again.
perfect.
Okay, thank you.
I'm planning career fair, so I won't be here next Wednesday.
Okay. All right. Could you send me a note?
Yeah, definitely. Okay.
All right,
Just wanted
thank you.
to.
Yeah.